Usually when we talk about like a camera taking a picture or a sensor detecting light, there's this underlying expectation of smooth continuity.
Right, yeah. Like it's just a steady stream.
Exactly. You picture this flowing river of light pouring through a lens, hitting a sensor, and just seamlessly painting an image on a screen.
It definitely feels intuitive. I mean, we experience light as a continuous, unbroken wave of information, right? It's just warming our skin or illuminating a room.
Yeah, it feels fluid. It
Yeah,
feels predictable.
yeah.
But when you zoom in, and I mean zoom way, way down past the macro world, down to the absolute fundamental limits of physics, that flowing river completely changes character.
It really does. It's not a river at all at that scale.
No, it's chunky.
Right, it becomes completely granular.
It's just individual droplets, single photons. And trying to catch just one of those droplets and actually
Yeah.
prove you caught it without the background noise just washing it out
Mm.
turns out to be one of the most incredibly difficult engineering challenges of the modern age.
Oh, absolutely. Catching a single photon completely upends how we traditionally think about electronic circuits. It forces us to redesign the physical traps we use to catch light, literally atomic layer by atomic layer.
Which brings us to the mission for today's deep dive. And I want to welcome a very specific group of listeners joining us for this journey. We are dedicating this exploration explicitly to the Busson Sigma Scholars of Edward Little High.
A warm welcome to all of you at Edward Little High up in Maine. It is a phenomenal topic to unpack today.
It really is. We've put together a custom-tailored journey just for you scholars. Diving into the deep end of semiconductor physics, we're going to trace the unbelievable evolution of the diode.
Starting right at the fundamental physics of how a basic diode works.
Exactly, the absolute bedrock of modern electronics. And from there, we're going to scale up the voltage and the engineering to see how these microscopic devices can detect single solitary particles of light.
And finally, we'll zoom all the way down to the nanoscale, looking at cutting-edge quantum dots that can actually capture individual electrons for advanced computing.
Okay, let's unpack this. Before we get to lasers or, single photon detectors, we really have to set the stage. Take us back to the very beginning. How did we even figure out the semiconductor p-n junction in the first place?
Well, the history here is wonderful because it proves that the greatest scientific leaps, they often happen by complete accident.
Wait, really? An accident?
Yeah. The very first high-efficiency semiconductor p-n junction wasn't theoretically modeled and then carefully constructed. It was literally stumbled upon.
Where and when did this actually happen?
So we are at Bell Telephone Laboratories in Holmdel, New Jersey. The year is 1940. And a metallurgist and radio pioneer named Russell All was working with silicon crystals.
Okay.
Now, context is super important here. In 1940, they did not have the ultra-pure, perfectly grown silicon wafers that we use today to make computer chips.
Right, the manufacturing just wasn't there.
Exactly. The silicon they worked with was grown in ingots, and it was just full of natural impurities.
So it was essentially dirty silicon.
Precisely. It was a mess. Ola was examining a particular silicon sample that had a visible physical flaw, like a crack right down the middle of it.
Just a broken piece of rock.
Yeah, but it wasn't just a mechanical fracture. Because of how the crystal had cooled, the concentration of different natural impurities had actually segregated.
Meaning, like, one type of impurity ended up on the left side of the crack, and a completely different type ended up on the right side.
Yes. And that created a natural boundary. So Ol was running electrical tests on it, and at one point he just shone a simple flashlight on this boundary.
Just a regular flashlight.
Just a flashlight. And when he did, he noticed something on his oscilloscope that completely defied the standard understanding of materials at the time. A spontaneous voltage spike appeared across the crystal.
Wait, just shining a flashlight on a piece of dirty rock created a measurable electrical voltage.
A very strong one. He had inadvertently created a p-n junction, and he was observing the photovoltaic effect. Without intending to, Ol had built the first modern solar cell and the first solid-state photodetector.
That is wild. But let's look under the hood of that crystal for a second. For the scholars listening, what exactly is happening at the atomic level that turns a flawed rock into a power source? Like, what is a p-n junction?
To understand the junction, we have to understand the two halves separately. So the p-type region and the n-type region. Let's start with just pure silicon.
Okay, pure silicon.
A silicon atom has 4 electrons in its outer shell. In a crystal, it shares those 4 electrons with 4 neighboring silicon atoms, creating a perfect, rigid, stable lattice.
So all the electrons are locked up.
Yeah, they're all locked into covalent bonds. Pure silicon is actually a pretty good insulator because there are no free electrons to move around and carry a current.
So how do we get the current to flow then?
We introduce those impurities all was dealing with. This is a process we now call doping.
Doping, okay.
Yeah. If we take a section of silicon and intentionally mix in a tiny amount of an element like phosphorus, which has 5 electrons in its outer shell instead of 4.
Then 4 of those electrons lock into the silicon lattice, right?
Exactly. But the 5th one, it has nowhere to bind. It just wanders loosely around the crystal.
So by adding phosphorus, we've injected free, mobile negative charges into the material.
Yes. And because electrons have a negative charge, we call this N-type silicon. Now, on the other side, we do the exact opposite. We dope the silicon with an element like boron, which only has 3 electrons in its outer shell.
So it's actually missing an electron to complete the lattice structure.
Exactly. It creates an empty spot in the bond. We call that empty spot a hole. And what's really fascinating is that this hole acts exactly like a mobile positive charge.
Wait, how does an empty spot move?
Well, if a neighboring electron jumps over to fill the hole, it leaves a new hole behind where it just came from.
Oh, I see. It's like a bubble in a bottle of water. As the water moves down to fill the space, the bubble appears to move up. The hole itself is just an absence, but it moves through the crystal like a physical, positively charged particle.
That is the perfect way to visualize it. So this gives us P-type silicon, named for its positive charge profile. Now, the magic of the p-n junction happens the moment you stick that P-type silicon and that N-type silicon together.
Okay, so you have a high concentration of free, wandering electrons on the N side,
Right.
and a high concentration of wandering holes on the P side. Do they just mix?
They do, yeah, driven by simple diffusion. Imagine opening a bottle of perfume in a room. The molecules naturally spread from high concentration to low concentration.
Right.
At the border, where the P and N regions touch, the electrons from the N side naturally wander across the border into the P side, where there are plenty of empty holes to fall into.
And when an electron falls into a hole, they essentially just cancel each other out, right?
They recombine, yes.
Yeah.
The mobile charge vanishes. But here is the critical mechanism that makes all electronics work.
Okay.
When that mobile electron leaves the N side, it leaves behind the phosphorus atom it originally came from. That phosphorus atom is locked tightly in the crystal lattice. It can't move.
Right, it's part of the structure.
But because it just lost an electron, that stationary atom is now a positively charged ion.
Ah, and I assume the exact inverse happens on the other side.
Yes. When the electron crosses over and fills a hole on the boron atom, that stationary boron atom suddenly has an extra negative charge. It becomes a fixed negatively charged ion.
So right at the border, all the mobile carriers are wandering across and canceling each other out. But in doing so, they are leaving behind this growing wall of fixed stationary positive charges on one side and stationary negative charges on the other.
Exactly. And because all the free carriers in this immediate border zone have annihilated each other, the zone is completely depleted of any mobile charge.
Hence the name, the depletion layer.
You got it. It acts as an insulator. But more importantly, because you have fixed positive charges on one side and fixed negative charges on the other, you have created a permanent electric field pointing across the junction. We call this the built-in potential.
I want to try an analogy here to make sure I'm wrapping my head around this built-in potential. Let's think of this electric field like a steep physical hill separating two flat planes.
Let's explore that. How does the hill affect the electrons?
Well, the hill pushes back. The electrons want to keep diffusing across the border. But now there's this electrostatic hill in the way. At some point, the hill gets so steep that the electrons just don't have the energy to climb it, and the diffusion stops. The system reaches equilibrium.
Yes, exactly. And that built-in hill is what gives the diode its one-way property.
Which is the whole point of a diode.
Right. If you hook a battery up to this crystal and apply voltage in the forward direction, what we call forward bias, the battery's voltage pushes against the built-in field. It essentially acts like a bulldozer, flattening that hill.
And once the hill is flattened, the depletion layer shrinks, the electrons can easily flow across, and the diode conducts electricity.
But if you flip the battery around and apply a reverse bias, you're pulling the planes further apart.
Oh, so the battery's voltage adds to the built-in potential.
Exactly. The hill gets much, much steeper, the depletion region widens, and it becomes this massive resistive wall. No current can flow at all.
Okay, I have to push back here.
Go for it.
If our goal today is to detect light, that means we need a sensor that can produce an electrical signal when light hits it. But you're saying a reverse bias diode acts like a giant wall that blocks all current. aren't we defeating the entire purpose? How does a blocked circuit become a sensor?
It sounds completely counterproductive, doesn't it?
Yeah.
But that wide, highly resistive depletion layer with its incredibly steep electric field is actually the perfect trap for a photon. Let's say your reverse bias diode is sitting there in total darkness.
Okay, total darkness.
Because of that massive hill, almost zero current is flowing. Now, one of our little droplets of light, a single photon, comes flying in and strikes the depletion layer.
What happens when it hits?
Well, if that photon has enough energy, it can crash into one of the silicon atoms locked in a lattice and knock an electron completely out of its covalent bond. We call this the photovoltaic effect.
So the photon is transferring its energy to the electron.
Right. In physics terms, it promotes the electron across the band gap. It bumps the electron up from the valence band, where it's stuck in a bond, to the conduction band, where it's free to move.
And remember, when you create a free electron, you leave behind a hole.
Yes. So one photon creates exactly one electron-hole pair right in the middle of our depletion layer.
But the depletion layer is exactly where our steep electric field is located.
Boom! The moment that electron-hole pair is created, they find themselves on that steep hill. The electric field instantly, violently sweeps them apart.
Whoa.
The electron is shoved in one direction down the hill, and the hole is shoved in the opposite direction.
And movement of charge is literally the definition of electrical current.
Precisely. This sudden, forced separation of charge creates a measurable, instantaneous current. We call it a photocurrent.
What's fascinating here is that this very basic mechanism, operating in what engineers call the third quadrant of the IV characteristic, the reverse bias region, is the absolute foundation for all the advanced photodetectors we are going to discuss today.
It really is.
Like Russell Ohl's happy accident laid the groundwork for everything from fiber optic internet receivers to the cameras on the Mars rovers.
It's the fundamental building block. But as revolutionary as the basic PN junction is, it has a severe limitation when you try to use it for highly sensitive applications.
Right, because if you are trying to detect incredibly weak light, maybe a signal that's traveled through the hundreds of miles of fiber optic cable, or like the faint glow of a distant galaxy, a standard PN junction just isn't going to cut it.
Not at all.
Why is it insufficient?
It really comes down to physical geometry. The usable absorption region, that depletion layer where the electric field is strong enough to separate the electron-hole pair before they just recombine and vanish, is quite narrow in a basic PN diode.
So it's microscopically thin.
Very thin.
It's just a tiny target. If a photon passes straight through the crystal without happening to hit an atom in that specific narrow depletion zone, it just goes completely undetected.
Exactly. So semiconductor engineers realized they needed to widen the net. They needed to make the depletion region physically thicker. To do this, they created the first major architectural upgrade, the PIN diode. PIN.
Okay, what does the I stand for?
Intrinsic. Instead of just putting the highly doped p-type and n-type regions right next to each other, engineers sandwiched a relatively thick layer of intrinsic semiconductor between them.
Intrinsic essentially meaning pure undoped silicon.
Yes.
How does adding a pure layer help?
Because it's undoped, it has very few free carriers of its own. So when you apply that reverse bias voltage, the electric field doesn't just form at a sharp boundary, it stretches out, propagating across that entire thick intrinsic layer.
Oh, so you have effectively stretched the depletion region.
You've made the steep hill wider.
Yes. The target zone is now considerably larger, dramatically increasing the probability that a photon will be absorbed in a region where the electric field can sweep the carriers away.
Okay, so we've made the target bigger. But I see another fundamental problem here.
Which is?
If we are looking for a single, solitary photon, even a beautifully engineered PIN diode only generates one single electron-hole pair per photon.
Right.
That means you get exactly one electron's worth of current. That is an infinitesimally small signal. How can standard electronic circuits even measure that above the natural static and thermal noise of the universe?
They usually can't. Not directly. We don't just need a bigger target. We need to turn up the volume on the signal itself. We need internal amplification within the diode.
And that brings us to the realm of avalanche photodiodes, or APDs. How do we get a diode to amplify its own signal?
We take that reverse bias voltage, the battery pulling the P and N regions apart, making the hill steeper, and we crank it to the absolute extreme.
Right to the edge of what the physical crystal can handle without being destroyed.
What happens to the physics inside the depletion layer when the voltage is that high?
You create an incredibly intense electric field. Now, let's trace our photon again. It enters the depletion region. hits an atom and creates that initial electron-hole pair.
Okay.
The electric field grabs that electron, but because the field is so ridiculously strong, the electron doesn't just drift out of the region, it accelerates violently.
It gains kinetic energy as it moves.
A massive amount of kinetic energy. And as it rockets through the crystal lattice, it eventually collides with another silicon atom.
Hmm.
Because our electron is moving so fast and possesses so much kinetic energy, that collision actually knocks another electron loose from its covalent bond.
Oh, so it creates a second electron-hole pair just from the impact.
Yes, this process is called impact ionization.
Let me bring back my hill analogy, but let's upgrade it to a steep, snow-covered mountain peak.
Let's see how it holds up.
That first photon hitting the crystal is like a hiker, packing a single tight snowball and rolling it down the peak. At first, it's just one snowball.
Right.
But because the mountain is so steep, representing our high electric field, that snowball gathers immense speed. It smashes into a clump of snow, dislodging 2 more snowballs.
And then those 3 snowballs keep rolling, accelerating, smashing into more snow.
Exactly. Before you know it, that one initial snowball has triggered an entire massive avalanche of snow rushing down the mountain.
And that multiplicative nature is exactly what happens with the electrons. One photon creates 1 electron. That electron triggers impact ionization to create 2. Those 2 accelerate and create 4, then 8, then 16.
Wow.
Within picoseconds, you have a self-sustaining avalanche of macroscopic current. You have amplified the signal of a single photon into a massive pulse of electricity that standard electronics can easily read.
And this is where we need to make a critical distinction about how you operate these avalanche photodiodes. The terminology here is linear mode versus Geiger mode. Let's break those down. What dictates which mode you are in?
It all comes down to exactly where you set that reverse bias voltage relative to the diode's static breakdown voltage.
What's the breakdown voltage?
It's the specific point where the electric field is so intense that the avalanche process becomes completely self-sustaining, generating infinite current until it basically burns out.
So if we are cautious and keep our voltage below that breakdown threshold?
If you stay just below the breakdown voltage, you are operating in linear mode. An avalanche still happens when a photon hits, but because the electric field isn't quite at the breaking point, the avalanche eventually fizzles out before it consumes the whole device.
So you might get an amplification factor, what we call gain of maybe 100 or 1,000 electrons per photon.
Yes. And I assume it's called linear because there is a proportional relationship.
Exactly. The total amount of current you get out is still roughly proportional to the number of photons that came in.
So if 10 photons hit simultaneously, they'll create 10 separate mini avalanches, yielding 10 times more current than one photon.
Right. The output scales linearly with the input light. But what if we abandon caution? What if we push the voltage above the breakdown limit?
Now you have entered Geiger mode. You are essentially operating the device in a highly unstable, supersaturated state.
Sounds dangerous.
It is. The electric field is so intense that the moment a single photon triggers that first impact ionization, the avalanche never stops. It runs away completely. You get a massive, fully saturated pulse of current.
So no longer matters if 1 photon hit it or 1,000 photons hit it. The output is exactly the same massive pulse.
Exactly. It ceases to be a proportional sensor and becomes a binary switch. 0 or 1, nothing, or avalanche. When an avalanche photodiode is specifically designed to operate in this supersaturated regime, we give it a special name, a STPA or single photon avalanche diode.
But wait a minute. If the avalanche in Geiger mode is truly self-sustaining and the current just keeps growing exponentially, wouldn't the heat generated just instantly melt the silicon? How does the device reset to catch the next photon?
That is the great engineering trick of Geiger mode. A SSP8 on its own is actually completely useless. It will just destroy itself the first time it sees light.
So what's the solution?
It requires a specialized external circuit to forcefully stop the avalanche before thermal runaway occurs. We call these quenching circuits, and there are 3 main types used in the industry today.
Let's walk through them, maybe starting with the simplest.
The simplest method is passive quenching. In this setup, you wire a very large load resistor in series with this SPA.
And for the scholars listening, a resistor just restricts the flow of current.
Right. Now, when this SPA triggers and that massive avalanche current starts flowing, it has to pass through that large resistor. According to Ohm's law, pushing a large current through a large resistance creates a large voltage drop across the resistor.
Ah, I see. Since the total voltage supplied by the battery is fixed, if the resistor is suddenly hogging all the voltage?
There is less voltage available for the SP8 itself.
Right.
The voltage across the diode is physically forced to drop below the breakdown threshold. The electric field weakens, and the avalanche naturally starves itself of energy and dies out.
That is incredibly elegant. The avalanche literally chokes itself out.
It is elegant, but there is a catch.
Always a catch.
Once the avalanche stops, the voltage across this SPA doesn't instantly snap back up. It has to recover slowly, dictated by the RC time constant of the circuit.
Let's clarify the RC time constant. That's resistance times capacitance, right?
Yes. Think of the SPA as a small water tank. That's the capacitance. And the load resistor is a very thin pipe feeding water into the tank.
Okay, I'm picturing it.
When the avalanche triggers, you basically pull the plug on the bottom of the tank and it drains instantly. But to reset the device, you have to put the plug back in and wait for the tank to refill through that thin pipe.
And because the resistor, is so restrictive, it takes a measurable amount of time for the tank to refill and the voltage to rise back above the breakdown point.
Precisely. And during that refill time, the detector is completely dead. It cannot detect another photon. If you need to count photons arriving very quickly, passive quenching is far too slow.
So how do we speed it up?
We use the second type, active quenching. Instead of waiting for a slow physical process, we use high-speed comparator logic circuits.
How does that work?
The moment the circuit detects the very leading edge of the avalanche current, the logic gate instantly, actively drops the bias voltage to quench it, waits a tiny fraction of a nanosecond, and then forcefully drives the voltage back up to reset it.
It actively manages the tank.
Exactly, making the dead time incredibly short.
And the third quenching method.
Gated quenching. This is used when you know precisely when your photon is going to arrive. You keep the constant DC bias voltage safely below the breakdown point. Then you superimpose a high-frequency rectangular electrical pulse on top of it.
So the voltage is constantly bouncing up and down, briefly crossing into Geiger mode, and then dropping back to linear mode.
Exactly. The device is only capable of triggering a self-sustaining avalanche during the brief on window of the pulse. If an avalanche occurs, the natural falling edge of the electrical pulse automatically quenches it a fraction of a nanosecond later.
This sounds perfect for something like quantum cryptography, where you are firing a laser pulse and you know the exact microsecond the returning photon should hit the detector. You only open the gate for that precise window.
Exactly. It completely limits the amount of time the device is vulnerable to noise.
Which brings up a massive point. If these SPEs are sensitive enough to trigger an unstoppable avalanche from a single photon, what happens if something else triggers the avalanche? Like, how do we evaluate how well these devices actually work in the real world?
Well, when engineers design a SPE, there are two primary metrics they are constantly fighting to balance. The first is SPDE, or single photon detection efficiency.
Which is just a measure of how good the trap is.
Exactly. If 100 photons hit the detector, what percentage of them will actually successfully create an electron-hole pair, initiate an impact ionization, and trigger a full avalanche? You don't want your SPDE as high as physically possible.
Okay, so that's the good metric. What is the bad metric?
The bad metric is DCR, or dark count rate. This is the ultimate enemy of the SPE.
What does that mean?
If you take your detector, seal it in a light-proof box, and put it in absolute pitch blackness, how many times per second does an avalanche spontaneously trigger anyway?
Wait, if it's in total darkness, there are no photons to start the avalanche. What is triggering it?
It isn't light. It is quantum mechanics and thermal energy.
Of course it is.
There are two main culprits that generate false avalanches, or dark counts. The first is band-to-band tunneling, which is sometimes called Zener breakdown.
How does tunneling work here?
Remember that when we are in Geiger mode, our electric field is incredibly intense. The quantum mechanical barrier separating the valence band from the conduction, the band gap, becomes extremely thin under such a high field.
Right.
And in quantum mechanics, particles don't always behave like solid objects. They behave like probability waves.
So instead of needing the energy to climb over the wall, the electron can just phase through it.
Yes. Because the barrier is so thin, there is a statistical probability that an electron simply tunnels directly through the band gap without needing a photon's energy at all. And once it appears on the other side, the electric field instantly grabs it, accelerates it, and you get a full avalanche.
Wow. So the detector screams, photon, but it was entirely a quantum illusion.
Exactly. The second mechanism is trap-assisted tunneling, or TAT-T. This happens because the semiconductor crystal is never structurally perfect. There are always slight defects in the crystal lattice or, unintended impurity atoms.
How do defects cause a dark count?
These defects create intermediate energy states right in the middle of the band gap.
Wait, if the band gap is normally a wide, empty canyon that an electron has to loop across all at once, what do these intermediate states do?
They act exactly like stepping stones in the middle of a river. Instead of needing one massive burst of energy to leap the entire canyon or tunnel through the thickest part of the barrier, normal ambient thermal energy in the room can pop an electron onto one of these stepping stones.
Oh.
From there, it's a much shorter, easier distance to tunnel the rest of the way across.
That makes total sense. The more structural defects your crystal has, the more stepping stones you have, making it vastly easier for ambient heat to push electrons across.
And your dark count rate goes completely through the roof.
Okay, so we've established how incredibly sensitive these silicon single-photon avalanche diodes are. But here is where we encounter a major physical roadblock. Yeah, a big one. Silicon is amazing for visible light and infrared, but what if you need to detect a very specific, extremely high-energy type of light, say the solar blind ultraviolet range? We're talking about wavelengths shorter than 280 nanometers.
This is where standard silicon technology completely falls apart. And it's frustrating because silicon CMOS technology is ubiquitous, it's cheap, the manufacturing is mature, we know how to grow the crystals perfectly.
But for UV detection, silicon is fundamentally the wrong material.
Completely wrong.
Why? I mean, light is just light. Shouldn't a good detector see all of it?
To a semiconductor, the wavelength of the light is everything because wavelength dictates energy. It all comes back to the band gap. Silicon has what is called an indirect band gap of about 1.12 electron volts, or eV.
Let's clarify what indirect means for the scholars.
In a direct band gap material, an electron just absorbs a photon and jumps straight up. But in an indirect band gap material like silicon, jumping the gap requires a change in momentum. The electron has to simultaneously absorb a photon and interact with a physical vibration of the crystal lattice to successfully make the leap.
It's a two-step process that has to align perfectly.
Yes. But more importantly, that 1.12 eV energy gap corresponds perfectly to the energy of photons in the near-infrared spectrum, roughly 650 to 850 nanometers. That is the sweet spot where silicon is most efficient at absorbing light.
So what happens when you shine high-energy ultraviolet light on it?
UV photons have much shorter wavelengths, which means they carry drastically more energy than infrared photons. Because silicon is optimized to absorb lower energy light deeply within the crystal, these extremely energetic UV photons get absorbed instantly right at the very surface of the silicon.
Often in the dead layer before they even reach the depletion region where the electric field is.
Exactly, they burn themselves out before they reach the trap.
And furthermore, if you want a silicon detector to only see UV light, say you're trying to detect a missile plume against a bright sunny sky, you have a massive problem.
Oh yeah. The sun floods the sensor with visible and infrared light, which silicon naturally loves to absorb.
So you'd have to put heavy optical filters over the lens to block out all the visible light.
Yes, complex, bulky, expensive filters. And even with filters, their responsivity, the amount of current they actually manage to produce per watt of UV light, is incredibly low. State-of-the-art silicon UV APDs barely register 0.14 amps per watt at 250 nanometers.
But the inefficiency isn't even the worst part. There's a much darker reality for silicon when exposed to UV. The energy of those UV photons doesn't just fail to be detected. It actively destroys the sensor over time.
It is a severe reliability issue. Those ultraviolet photons pack so much punch that when they smash into the surface of the silicon lattice, they have enough energy to literally break the covalent bonds holding the crystal together.
Wow, they just shatter the lattice.
They create what we call dangling bonds and trap states right at the interface. Over time, as you expose the sensor to UV, you are dynamically creating more and more of those stepping stones we talked about earlier.
Which means the dark count rate skyrockets and the sensor just drowns in its own noise.
Exactly. If you look at reliability studies on commercial silicon UV APDs, their efficiency and noise performance plummet rapidly after prolonged UV exposure. They get sunburned.
We clearly need a completely different material.
Enter silicon carbide, specifically the 4HCC polytype.
4HCC.
Yes. This is a wide bandgap compound semiconductor, and it elegantly solves almost all of silicon's problems for UV detection.
Walk us through the band gap difference.
Where silicon has a bandgap of 1.12 eV, 4HC has a massive wide indirect bandgap of about 3.25 eV.
That is nearly 3 times as large. What does that mean practically for a photon trying to cross it?
It means that low-energy photons, like all visible light and infrared, simply do not possess enough energy to promote an electron across that massive 3.25 eV gap. It is physically impossible for them to be absorbed.
They just pass right through the material, as if it were perfectly transparent glass.
Precisely. And because of that, Synesy is intrinsically solar blind. You don't need heavy filters because the material itself naturally ignores the background noise of the sun's visible light.
And what about the sunburn issue?
Because the atomic bonds between silicon and carbon in the Synesis lattice are exponentially stronger than the bonds in pure silicon, it is incredibly robust and radiation resistant.
So the high-energy UV photons can't shatter the bonds and create defects.
Right. It does not degrade under UV illumination. It can operate in extreme heat and high radiation environments for years without issue.
But when researchers were first developing these Synesic APDs, they had to prove that the avalanche they were measuring was actually true impact ionization, and not just massive Zener tunneling leaking through that wide band gap. How do you prove what is causing the current?
You test the device at different temperatures. This is a vital diagnostic tool. A true avalanche breakdown driven by impact ionization has a positive temperature coefficient.
Meaning, as the device gets physically hotter, the voltage required to trigger the avalanche goes up. Why would heat make it harder to trigger?
It goes back to the crystal lattice. When you heat up the material, you add thermal energy. The atoms locked in the lattice start vibrating more violently. These physical vibrations are quantized as particles called phonons.
Okay.
Now, imagine our electron trying to accelerate through the electric field to gain enough kinetic energy to knock another electron loose.
Our snowball rolling down the steep mountain.
Yes, but now, because you've heated the material, the lattice is vibrating wildly. It is like the mountain is suddenly covered in a dense forest of shaking trows. The electron keeps bumping into the vibrating atoms, what we call phonon scattering.
And every time it bumps into a vibrating atom, it loses its momentum and its kinetic energy.
Exactly. Because it keeps losing energy to scattering, you have to apply an even stronger electric field, a higher reverse bias voltage, to force it to accelerate fast enough between collisions to cause impact ionization. Therefore, the breakdown voltage naturally goes up with heat.
And if the current was being caused by tunneling instead?
Tunneling breakdown has a negative temperature coefficient. Heat provides thermal energy, which excites the electrons a little higher up, making the barrier effectively thinner. So as heat goes up, tunneling breakdown voltage goes down.
Ah.
By checking this, engineers confirmed SiC can support true avalanche multiplication.
Okay, so silicon carbide is a miracle material for UV. We just swap it in on the manufacturing line and start printing sensors, right?
If only were that simple. Building a functional SiC APD requires intense, highly specialized engineering, largely because of how electric fields behave at the geometric edges of micro devices.
Let's talk about the edges. What happens to the electric field there?
It's a phenomenon called electric field crowding. Imagine the diode as a flat, raised mesa structure etched onto a chip. At the sharp physical corners of that mesa, the electric field lines bunch up very tightly.
Okay.
The field density becomes astronomically higher at the outer edges than in the flat center of the device.
Which means if you start cranking up the reverse bias voltage, those sharp edges are going to reach the breakdown point long before the center does.
Exactly. The device will always prematurely break down at the edge, causing a massive short circuit. The avalanche happens on the periphery, not in the active center area where the light is actually hitting.
How do you fix that?
Engineers use structural techniques like beveled mesa structures. Instead of etching the sides of the device straight down to form a sharp box, they etch the sides at a very specific, highly controlled, shallow angle.
So it looks more like a gentle pyramid than a block.
Yes, this gentle slope forces the depletion region to spread out widely at the edge. By spreading it out, it drastically reduces the electric field crowding, ensuring the field remains strongest in the center bulk of the material where you want the avalanche to happen.
But the engineering goes even deeper than the physical shape of the sides. Let's look at the internal layers. Modern SiCos APDs utilize something called a SACM structure. SACM. Unpack that acronym for us and why is it necessary?
SACM stands for Separate Absorption, Charge, and Multiplication. To understand why it's vital, think about the two completely conflicting things we need our electric field to do inside the diode.
Okay, conflict one. To get a good avalanche, we need an incredibly high electric field.
Right. But conflict two. If the electric field is too high in the region where the light is being absorbed, you trigger massive amounts of Zener tunneling noise, which ruins your dark count rate.
It's a paradox. You want a massive field for amplification, but a low field to prevent noise.
Precisely. So the SACM architecture physically separates these two functions into different layers. First, you grow a thick, lightly doped absorption layer.
Okay.
Because it's lightly doped, the electric field here is naturally kept relatively low and safe. The UV photon hits here and creates the electron-hole pair without triggering tunneling noise.
And then the field pushes that newly created electron into a different layer.
Yes, it gently drifts the carrier into a separate multiplication layer.
Yeah.
This layer is very thin, and the electric field here is astronomical perfect for impact ionization.
Wait, how is that physically possible? How do you have a low electric field in one layer and a massive electric field in the layer right next to it? Shouldn't the field just average out across the material?
That is the genius of the charge layer, the C in SACM. Engineers grow a highly doped, ultra-thin layer exactly between the absorption zone and the multiplication zone. This charge layer acts as a traffic cop for the electric field.
How does doping control the field?
It comes down to Gauss's law. The high concentration of static dopant ions in that ultra-thin charge layer firmly anchors the electric field lines. It allows the field to spike massively on the multiplication side of the layer, but the charge layer absorbs all that flux, abruptly dropping the field down to a safe low level as it crosses over into the absorption side.
That is astonishing. We're manipulating atomic doping profiles nanometer by nanometer to choreograph exactly how an electric field behaves across different microscopic layers.
It is truly a masterclass in semiconductor device physics and material science.
We have manipulated the layers of materials to control electric fields. But what happens when we manipulate the geometric dimensionality of the material itself?
Now we are stepping fully into the quantum realm. Over the last few decades, there has been a fascinating evolution from 3D bulk materials down to 2D structures and finally to 0D structures.
For the scholars trying to picture this, let's walk through that dimensional shrinkage.
In a traditional bulk semiconductor, what we consider 3D electrons are free to move in all three spatial dimensions, X, Y, and Z. Their energy states are continuous bands.
Right.
But as our manufacturing advanced, we developed techniques like molecular beam epitaxy, or MBE.
Explain MBE. How do you grow these materials?
MBE is an ultra-high vacuum technique where you are essentially spray painting individual atoms onto a heated crystalline substrate.
Spray painting atoms.
Yeah. You heat up ultra-pure elements until they form a gaseous beam, and you direct that beam at the surface, growing the crystal perfectly, one single atomic layer at a time.
And because you're growing it atom by atom, you can change the material instantly.
Exactly. We learned how to grow a very thin layer of a narrow bandgap material and sandwich it between two thick layers of a wider bandgap material. Now, if you make that middle layer incredibly thin, comparable to the de Broglie wavelength of an electron, just a few nanometers thick, something strange happens.
The de Broglie wavelength, this is the idea that matter, like an electron, isn't just a hard point, but actually acts like a fuzzy wave of probability.
Yes. When the physical thickness of that middle layer becomes smaller than the electron's probability wave, the electron physically cannot move in the z direction anymore. It is confined. It can only move freely in the x and y planes.
This is a quantum well, 2 dimensions.
Yes, and because of this quantum confinement in the z direction, the energy states are no longer continuous bands. They become discrete, quantized steps, like rungs on a ladder. We built quantum well infrared photodetectors, QWIPs, utilizing these exact discrete energy steps to absorb specific wavelengths of light.
But the evolution didn't stop at 2D. Why did we need to keep shrinking?
Because quantum wells have a very frustrating physical quirk based on quantum mechanical selection rules. A quantum well simply cannot absorb light that is shining straight down on it, what we call normally incident light.
Why not? If the light hits the well, shouldn't it get absorbed?
In quantum mechanics, for the photon to interact with the electron and bump it up to the next energy rung, the electric field vector of the light wave has to be aligned with the direction of confinement. Since a quantum well is only confined in the z direction, the light must have a polarization component in the z direction.
Which means you have to shine the light at a weird, steep angle to get any absorption.
Yes. Or, to make flat camera sensors, manufacturers had to etch incredibly complex, expensive optical gratings onto the surface of every single pixel to artificially scatter the incoming light sideways into the wells. It was a massive manufacturing headache.
So we need to confine the electron even more to solve the light angle problem.
Enter the quantum dot. This concept was first suggested by researchers Arakawa and Sakaki back in 1982. Instead of growing a flat 2D, imagine using MBE to grow tiny, nanometer-sized droplets or islands of material.
Okay.
Now the electron is confined in X, Y, and Z. It cannot move freely in any direction whatsoever.
Zero dimensions.
Exactly. The energy states are now fully discrete in all three directions. The density of states is entirely quantized, looking very much like the discrete electron orbital shells of a single isolated atom, which is why quantum dots are frequently referred to as artificial atoms.
And how does this artificial atom solve the light angle problem?
Because the electron is confined in all three dimensions, those restrictive polarization selection rules vanish. Quantum dots can easily absorb normally incident light. You can shine light straight down onto a flat quantum dot infrared photodetector, and it absorbs it perfectly. No expensive gratings required.
Beyond solving the angle problem, there are massive performance boosts we get from going to 0D. Let's explore those.
One of the most critical advantages is the minority carrier lifetime. In a 2D quantum plane, when an electron gets excited by a photon, it tends to lose that energy and fall back down to its ground state very quickly. We're talking single-digit picoseconds.
It doesn't survive long enough in the excited state to be swept away as a measurable electrical current.
Exactly. But in a 0D quantum dot, because the energy levels are so perfectly discrete and spaced out, it is much harder for the excited electron to find a crystal vibration of the exact right energy to help it shed its heat and relax back down.
It's like trying to walk down a staircase where the steps are suddenly spaced 10 feet apart.
Yes. This phenomenon is called the phonon bottleneck. As a result of this bottleneck, the minority carrier lifetimes in QDIPs are significantly longer, often on the order of 100 picoseconds to a full nanosecond.
And a longer lifetime means.
It translates directly to higher photoconductive gain.
Hey.
The electron survives in the excited state long enough to be successfully swept out of the active region by the electric field and registered as a signal. It also allows these quantum dot devices to operate at much higher temperatures while maintaining dramatically lower dark currents than their quantum well predecessors.
Okay, but let's talk about the physical layout of these dots in a real device, because they aren't just a uniform sheet of material. I'm imagining a microscopic pegboard.
Let's follow that visual.
With a 2D quantum, the whole board is sticky. A photon hitting anywhere on the flat surface can interact. But with quantum dots, because they are discrete islands, only the individual pegs sticking out of the board are sticky. The spaces between the dots are just dead space. How does that affect the overall efficiency of the sensor?
You've hit on a crucial mathematical and engineering metric known as the fill factor. Because the quantum dots are discrete, self-assembled islands scattered across a flat surface, they do not cover 100% of the area.
Right.
We have to mathematically calculate the specific volume of the active quantum dots relative to the total volume of the epitaxial layer they sit in.
Because if your dots are too sparse, most of your incoming light just passes right through the empty space between them without ever being detected.
Exactly. Maximizing that fill factor, figuring out how to use MBE to pack the dots as densely as possible without them accidentally merging together into a 2D well and losing your 0D confinement, is one of the primary material science challenges in creating highly efficient QDIPs. You need enough pegs on the board to ensure the photons actually strike one.
We know quantum dots can act as amazing sensors. We know they are basically artificial atoms. But how exactly do they capture and hold on to the electrons? And more importantly, how long does that capture process take?
Right.
If we want to use these structures for ultra-fast communications or computing, speed is the most critical metric.
This is where we get into some truly bleeding-edge optoelectronic research. We have to look at carrier capture delay, specifically in devices like edge-emitting quantum dot lasers.
Set the scene for us. What is the physical setup inside one of these lasers?
In these complex laser structures, you don't inject the electrical carriers directly into the tiny quantum dots. The dots are simply too small. It's practically impossible to route wires to them.
So what do?
Instead, you inject the carriers into a larger, thicker surrounding region called the optical confinement layer, or OCL.
So the OCL is acting like a large waiting room.
Yes. The electrons enter the OCL waiting room, and they have to randomly diffuse around the material until they happen to physically encounter and fall into the potential well of a quantum dot. This capture process is not instantaneous.
It takes time for the electron to find the door.
Exactly. And the physics models show that this non-instantaneous capture delay actively limits how fast you can turn the laser on and off, what we call the high-speed modulation bandwidth.
Oh, okay.
The math uses a parameter called the capture cross-section to model how easily a dot can grab a passing electron. If the cross-section is large, capture is fast. But as the physical dimensions of the dots shrink, the capture cross-section decreases, the capture delay increases, and the maximum speed of the laser plummets.
This delay literally acts as a hard speed limit on the device. It dictates the fundamental upper limit of how fast a quantum dot laser can transmit data down a fiber optic cable.
It does. It is a massive hurdle for telecommunications.
But all of this is mathematical modeling. We are talking about individual electrons randomly falling into nanometer-sized islands. We can't actually see that happen in real life, right?
And prepare to have your perspective shifted. In a landmark experiment at Uni Duisburg Essen, scientists actually managed to watch, in real time, a single self-assembled quantum dot capture a single free electron.
How do you watch a single electron? You can't put it under a standard microscope.
You don't watch the electron directly, you watch the light it interacts with, using a technique called time-resolved resonance fluorescence.
Resonance fluorescence.
Yeah. They shine a highly stable, continuous wave laser onto a single, isolated quantum dot. And they tune the frequency of that laser perfectly, resonantly, to the exact energy required to create an exciton inside the dot.
And exciton is that bound electron-hole pair we talked about earlier.
Yes. The laser hits the dot and promotes an electron, creating the exciton. A fraction of a nanosecond later, the exciton naturally recombines and emits a photon back out. The laser instantly creates another exciton, it emits another photon.
So the dot is constantly absorbing and emitting. It is glowing steadily. It's fluorescing.
Exactly. The scientists are monitoring this steady stream of fluorescence. Now, the dot is embedded in a diode structure that has a highly doped back contact.
Okay.
By using a second, completely separate off-resonance laser pulse, the scientists deliberately excite free photoelectrons from that back contact into the surrounding material.
So they have purposefully injected free electrons into the waiting room around the glowing dot.
Yes. And eventually, one of those free wandering electrons gets trapped. It falls into the potential well of the quantum dot.
What happens to the steady glow of the dot when it catches that extra unexpected electron? Does the glow change color?
The dot goes completely instantly dark.
Dark. Why would adding an electron turn it off?
Because of the Pauli exclusion principle and Coulomb interactions?
Let's break those down. What is the Pauli exclusion principle doing here?
The principle states that no two identical fermions-like electrons can occupy the exact same quantum state simultaneously. It's like trying to park two cars in the exact same parking spot.
Makes sense.
When that extra free electron falls into the dot, it occupies the lowest available energy state. Now, the dot is no longer neutral, it is charged. It has formed what is called a trion state, 2 electrons and 1 hole.
And how does that stop the fluorescence?
Because the dot is now negatively charged, the Coulomb force, the electrostatic repulsion between the newly trapped electron and the electron our laser is trying to excite, causes the fundamental energy levels of the artificial atom to shift slightly.
Oh, and because our viewing laser was tuned perfectly to the original uncharged energy level.
Exactly. The trapped electron detunes the system, it quenches the excitant transition. The dot essentially goes blind and deaf to that specific laser frequency. The scientists are watching their monitor, seeing a bright, steady signal, and then snap, the signal drops completely to 0. That instantaneous drop is the exact moment the single electron was captured.
That's profound. They're watching a single artificial atom capture a single electrical charge in real time just by watching it blink out.
And it stays dark until that captured electron eventually manages to quantum mechanically tunnel back out of the dot into the surrounding charge reservoir.
How long does it stay trapped before it tunnels out?
In this specific device architecture, with thick tunneling barriers engineered around the dots, the electron remains trapped for milliseconds.
Milliseconds. That is an absolute eternity in the quantum realm.
It is an eternity. It demonstrates vividly that even in highly controlled resonant optical setups, unintended free carriers can be generated, get captured by the artificial atoms, and severely disrupt the optical properties of the entire system for macroscopic amounts of time.
So an unintended electron ruins the optical party. But what if we did it on purpose? What if the capture wasn't an accident? This introduces the ultimate evolution of this mechanism, the OCDIP, or optically controlled quantum dot infrared photodetector.
This is where scientists turn a problematic quirk into a revolutionary feature, because quantum dots have those beautifully discrete energy levels, a ground state, a first excited state, a second excited state, and so on. We can use an external pumping laser to intentionally inject carriers and deliberately fill up the ground state of the quantum dots.
We are artificially doping the artificial atoms, but using light instead of chemical impurities.
Precisely. We aren't relying on boron or phosphorus like Russell Ohl did. We are using photons to precisely inject charge into the lowest energy states.
Let's trace the logic here. If we fill up the ground state of the quantum dot with one laser,
Once the ground state is completely full again, dictated by the Pauli exclusion principle, any new electrons arriving at the dot cannot go into the ground state. They are forced to occupy the first excited state.
and if there are now electrons sitting up in the first excited state, they require a completely different lower amount of energy to jump out of the dot entirely into the continuum.
Yes. By using a strong pumping laser to fill the ground state, we structurally unlock a second, entirely different absorption band. The dot can now absorb a new wavelength of light that it couldn't see before.
We are using one color of light, the pump laser,
Yeah.
to dynamically switch what color of infrared light the quantum dot detector can actually detect.
We have created a dual-band, optically switchable detector. You can toggle its sensitivity back and forth between two different infrared wavelengths just by turning a pump laser on and off. It is the absolute pinnacle of dynamic optoelectronic control at the nanoscale.
What a monumental journey. For you scholars listening, let's summarize exactly how far we have traveled. We started in 1940 with a scientist staring at a physical crack in a dirty silicon crystal, discovering the accidental p-n junction and the photovoltaic effect.
And from there, we took that basic built-in electric hill, widened it with an intrinsic layer, and then cranked the reverse bias voltage to the absolute breaking point to trigger massive self-sustaining single photon avalanches.
Then we realized silicon degrades under high energy, so we upgraded our materials to the wide bandgap silicon carbide to survive the harsh UV spectrum.
And we engineered complex SACM layers to act as electric field traffic cops to balance amplification against quantum tunneling noise.
And finally, we shrank everything down, from 3D bulk material to 2D quantum wells to zero-dimensional quantum dots, giving us artificial atoms where we can literally watch single electrons be captured in real time and even use light itself to dynamically reprogram what the detector can see.
It highlights a beautiful symmetry. Mastering the absolute tiniest, most ephemeral components of our quantum universe is exactly what allows us to build most macroscopic, world-changing technologies.
As we wrap up today's deep dive, I'm going to pass it over to our expert to leave you with one final thought to ponder.
Well, if we can use light to dynamically alter the fundamental energy states of a quantum dot, and we can watch it capture and hold a single electron in real time, we aren't just building more sensitive cameras. We're looking at the foundational mechanics of artificial logic. Imagine networks of these optically pumped quantum dots. Could they eventually replace traditional physical wired logic gates entirely? We might be looking at a future where processors route complex data not through physical copper wires, but through carefully choreographed nanoscale flashes of light, toggling artificial atoms on and off at the speed of photons.
To the Buzz and Sigma scholars of Edward Littlehigh and to all our listeners, thank you for exploring this with us. Keep questioning the microscopic world around you because you never know what you might accidentally discover.